In this video, we're going to look at how to write electron configurations using the periodic table. So you'll see that different sections of the periodic table correspond to the different subshells, S, P, D, and F. And we are going to write electron configurations by reading the periodic table like a book. So we're going to read the periodic table from left to right and top to bottom. We're also going to look at how to write electron configurations using noble gas notation, which is a shorthand type of notation. All right, so here's the periodic table, and you'll notice that we've got the different sections colored for the different blocks, the different subshells, S, P, D, and F. And notice that helium over here is the same color as the block on the left-hand side. This is our S block, and so we're going to look at helium, even though it's on the right in the periodic table, as belonging over here in what we call our S block of the periodic table. So the orange colored block here is our S block. Over on the right, this block over here is our P block of the periodic table, so that corresponds to the orbitals in the P subshell. The transition metals, these are our D orbitals, our D subshell. And the lanthanides and the actinides, this is our F block, so this corresponds to electrons that are in the F orbitals. So also notice that the position of the lanthanides and the actinides is sandwiched in here in between the S and the D block. So if we look at, once we get to element 56 right here, which is in our S block, we then go down to the lanthanides and actinides, and we get to 57. As we go across the row here, then we get up to 70, and we come back then up to the D block. And so we're going to have to keep this in mind as we read the periodic table as like a book from left to right. We'll have to remember that once we hit element 56, we have to jump down to the lanthanides and actinides, go across there, and then come back up to our D block. So every row of the periodic table is a period, and you'll notice that period 1 corresponds to principal energy level 1, N equals 1. Period 2 corresponds to N equals 2. Period 3 corresponds to N equals 3, and so on as we go down the periodic table. So we'll look at the S subshell. So remember, S orbitals can hold a total of 2 electrons, 1 spin up and 1 spin down. So that first electron, the S1 electron, corresponds to that first column of the periodic table, and the second electron that fills that S orbital corresponds to the second row of the period, or the second column of the periodic table. So the S block has 2 columns because you can put 2 electrons into an S orbital. The P subshell is made up of 3 orbitals, so it can hold a total of 6 electrons. So the first electron, P1, corresponds to this first column of the P block. The second electron, P2, corresponds to that second column. P3 corresponds to the third column, and so on. P4, P5, and P6. So you'll notice that there are 6 columns in the P block because you can hold a total of 6 electrons in the P subshell. All right, now we're going to look at the D block and the F block. So you'll notice that the energy level we had, this is N equals 3, and so this was S3. This is N equals 4. So for the main group elements, this corresponds to 4S and 4P. But when we get to the transition metals, the energy levels are actually offset by 1. So this row here are the N equals 3. These are the 3 Ds. Here we're in N equals 4, the 4 Ds. So even though the main group is energy level 5, the transition metals in that row are in N equals 4, and so on. So the D subshell has 5 orbitals. It can hold a total of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in total. And if you count the number of rows, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those correspond to the 10 different electrons that fill up the D subshell. If we look at the lanthanides and actinides, now you'll notice that the energy level is actually offset by 2. So with the transition metals, the energy level is offset by 1. Here they're offset by 2. If I'm in N equals 6, for the main group, I'm in 6S over here. And then I come down and I'm in 4F. So as I go across the periodic table here, I'm in 4F. And then I come back up to my D block and I'm in N equals 5 as I go across here until I hit my main group again, in which I return to N equals 6. So all of the F blocks are offset by 2, and all of the D blocks are offset by only 1. So I have to keep this in mind as I read the periodic table from left to right, because here I go from 6 down to 4, up to 5, and then back to 6 again. And the F block, the F subshell, can hold a total of 14 electrons. 1, 2, 3, 4, 5, 6, 7 orbitals can hold a total of 14 electrons. And you'll notice that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns in the F block of the periodic table. So again, those correspond to each of the 14 electrons that go into an F subshell. So now we're going to look at how I use this to write electron configurations for elements without having to memorize the ordering of the energy ordering of the orbitals. So we're going to use sulfur as our first example. So sulfur is element number 16, 16 protons. So neutral sulfur has 16 electrons. So I'm going to start at the very top of the periodic table, the very left-hand corner, and start to write my electron configuration using the periodic table like a book. So this would be the 1s1. This is the 1s2. Now I come down to the next row. Now I'm in 2s. So this would be 2s1, 2s2. Now I go across and I'm in my 2p's. So I have 2p, 1, 2, 3, 4, 5, 6, 2p6. And remember, p subshell is going to only hold 6 electrons. Then I come down to the next row. Now I'm in n equals 3. I'm in my 3s. I've got 3s1, 3s2. And then I go across and I'm in my 3p's. 3p, 1, 2, 3, 4. 3p, 4. So if I count the number of electrons, I have 2 plus 2 plus 6 plus 2 plus 4 gives me 16 electrons in total for sulfur. So without having to memorize that after 1s comes 2s, then comes 2p, then comes 3s, I'm reading the periodic table from left to right in order to get those energy orderings. This becomes particularly helpful as I get higher up in the periodic table. So we'll look at vanadium as an example once we start to get into the D block. So instead of having to memorize all these orbitals, I can use the periodic table. So we're going to do the same thing that we did for sulfur. Vanadium has 23 electrons. I start at the top, 1s2. Then I move down to the next row, 2s2. Then I go across, 2p. 1, 2, 3, 4, 5, 6. That's 2p6. Down to the next row, 3, 3s2. Go across to the 3p's. 3p, 1, 2, 3, 4, 5, 6. 3p6. Then I go down to my row 4, n equals 4. 4s2. And now I'm in my D block, so I need to remember instead of being an energy level 4, I'm actually in energy level 3. So this is 3d. 1, 2, 3. This is 3d3. So that is my electron configuration for vanadium. All right, let's look at one that's a little bit farther in the periodic table. We'll look at one that's in the F block. So we'll do the same thing. So this is going to be a very long configuration, but this will be good practice. So P promethium has 61 electrons. So I start at the top, 1s2, move down to the next row, 2s2, go across, 2p, 1, 2, 3, 4, 5, 6, go down to the next row, 3s2, go across in my 3p, 1, 2, 3, 4, 5, 6, down to the next row, I'm in my 4s2. Now I'm in my 3ds. So 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now I'm back into my main group. So now I go up to 4p. 1, 2, 3, 4, 5, 6. 4p6. Now down to the next row. I'm in energy level 5, row 5 of the periodic table. So 5s2. And now I'm in my 4ds. 4D, if I go across here, that's 10 altogether. Now I'm back in my P block, so I'm back up to energy level 5. 5P6. 1, 2, 3, 4, 5, 6. Now down to the next row, 6, energy level 6, S2. And now I hit that area where I have to go down to my F block. So I have 6S2, and now I have to go down to my Fs, and my F energy levels, we said, were offset by 2. So instead of being 5, it's 4. 4F, 1, 2, 3, 4, 5. 4F5. So a very long energy or electron configuration. If I count the total number of electrons in there, I should add up to 61. So because these become very long as I get farther down in the periodic table, we are going to look at how we use noble gas notation as a shorthand. So in this case, we're going to look at promethium again down here, element number 61, but I'm going to use the shorthand notation. So I always want to use the closest previous noble gas. So element number 61, the closest previous noble gas is xenon. So I'm going to start with xenon in brackets, and that represents all of the electrons through electron 54. So that's the first 54 electrons in my configuration. So now I can just go from xenon forward and figure out what are the rest of the electrons that go in that configuration. So after xenon, I would move down to row 6 of the periodic table. So I have 6s2, and then here I go down to my F block. So I have 4f, 1, 2, 3, 4, 5, 4f5. So you'll notice that the very end of the configuration here is what's showing in my shorthand notation, and xenon represents all of the electrons here. So instead of having to write all of those, this is my shorthand notation. Xenon just means the first 54 electrons in my configuration. So we'll try this one more time, one more example. We'll look at iron, which is element 26. So the closest previous noble gas is argon. So if I put argon in brackets, that represents the first 18 electrons in my configuration, and I only have to show the electrons that come after that. So after argon, which is in row 3, period 3, I move down to period 4. So I'm in my 4s, so that's 4s2, 4s2. And then I come over and I'm in my 3ds, 3d, 1, 2, 3, 4, 5. So my electron shorthand notation, noble gas notation for iron is argon 4s2, 3d5.